half of use, it starts to struggle um, with um, with audio, and there's actually a number of things I have to do to protect your privacy. I learned like I've got to um, it's a process, right? Like I got to start up the software here, and then turn off two things here, and then start the other copy of the software and sign into the room, and then I got to come back here and then move the chat window and the participants window and so on to the other screen so that it doesn't pop up if somebody chats, and because that'll show up in the recording even if it doesn't show up in the live version. And then there's one other thing. Oh, right. And then once I've signed in, there's going to be like a little video window here that yeah, there's a number of steps. So I'd like resetting is anyway, new device, like new thing. I'm wearing this like headphones slash earpiece combined kind of thing. I feel like an air traffic controller or something. I don't know. What should I say? Speedbird 1, fly heading 090. Yeah, that's actually a thing they say. Speedbird BT Dubs is the call sign of British Airways. Um, One of my favorite call signs. This is so nerdy. Why am I saying this? Why not? Well, because I've got 56 seconds. That's why. I didn't even tell the other section, but I guess everybody has access to the recording. One of my favorite call signs is no longer in use. U.S. Airways was swallowed up by American Airlines, but U.S. Airways itself, back when it technically existed, swallowed up an airline called America West, which was based in Phoenix. And so U.S. Airways adopted the America West call sign, which was cactus. There, just random useless knowledge. In fact, you remember that plane that landed in the river in New York City? It was Cactus 1549, if you listen to the air traffic control recording, which I did not ever do. All right, 15 seconds, huh? Oh, I need to rewind this thing here. Let's do that. Okay. All right. Good morning, folks. Welcome. And just for announcements, please, today's Wednesday, April 8th. It is the day before the technical date of the exam, so please complete the pre-exam assignment. Just inventory. It's meant to be easy points, but you get to inventory what things you think will be most challenging about the exam and what you're going to do about it. Thursday is the date of the exam, but you don't have to take the exam on Thursday if you don't want. So between Thursday and Friday, between that 48-hour time frame, you've got to pick a 5-hour time frame in which to start, and then by the end of that 5 hours, turn in the things for the exam. So as soon as you click start, there's a 5-hour countdown that'll go, and then you just work on it, maybe an hour, maybe an hour and a half, maybe two if you want, but like don't overdo it. You've got other things to do, I'm sure. Then take the pictures, upload those things, and then hit submit. I hope that the process start to finish for you is not 5 hours. I hope it's more like an hour and a half, or, maybe an hour and 40 minutes, something like that. I don't want it to take a lot of extra time on your part. Tomorrow, the question already came up is what about are we meeting for class at this time tomorrow? And no, we are not. So if you want to wake up early at around this time or even earlier and take the exam, that's fine. If you've got that block of time, or if you're going to just do it later in the day, that's fine. But I'm not going to be here and explaining some math at this time tomorrow, right? Like I am only going to sign in just to put a note on my screen that says I'm not actually here. Like I've got other things to do. I'm behind in grading, not only for you all, but in my other class. So I'll just be doing some grading. There's no point in burdening you with an extra class day. I don't want to take advantage of that in that fashion. Standard slide here for office hours again. Please drop by office hours. I'm glad I made the comment yesterday. I did get a couple more folks showing up. If you have an audio issue during office hours, please call the office phone number. Use a Murphy Learning Center. And now let's talk our way through what we're doing today. Today is going to not sound much like calculus because it's not. There will be very, very little calculus today. Today's story is not at all like yesterday or the day before or so on. But let's set the stage. Like, what are we doing and why are we doing it? At the end of last week, we talked about finding local mins and maxes. The short version is at each critical point, you need either the first derivative test or the second derivative test. Then at the beginning of this week, on Monday and Tuesday, we talked about finding absolute mins and absolute maxes. So that the process is different. In summary, you need the actual y values, right? So for absolute mins and maxes, like if you had the graph, you'd be like, where's the tallest, or I mean, where's the highest point and where's the lowest point? And so that's why you've got to plug into f. You need the actual y values. It's a common error to want to plug into f prime. And you'll even notice for the thing last week, local mins and maxes, you would plug into f prime if you're using the first derivative test, if you're making a sign chart for f prime. So it's because the first derivative test is doing different things. It's just telling you if there's a peak or valley. It's not telling you if you're getting to the highest point or not. So to see if you've got the highest point or not, you've got to look at the actual y values. So that's what we did last Wednesday, Thursday with local mins maxes, and this Monday, Tuesday with absolute mins and maxes. And both of these major procedures are used in what I would call maybe like a super procedure, that like you've got to pick what's most appropriate next week in these things called optimization problems. So what I learned from teaching this, I think this is the 6th time I'm teaching 175. I would have to check. But I'll say this about optimization right now. These are word problems. Word problems that might be worded like, find the X that causes the least amount of pollution, or find the X that makes the company the most profit, and so on. There are other optimization problems out there. I mean, I told the other section this, and I need to mention that so as faculty members, we don't just teach. I mean, that is where I spend most of my working week, but we are expected to do research as well. It turns out that my research area one of them is optimization. And so from a standpoint as a researcher in the area, I can tell you there's hundreds, thousands of optimization problems. So we're going to present not all of these. That's just too many. I don't want to burden you to like learn the lingo, the terminology in this area and that area and so on. But like at the same time, I don't want you to tune out. I think it's too easy to take the approach of, well, if I don't see a way that this is used for my future career goals, then it's not worth having as a question. And I don't think that's the right approach. Because if you dropped by an online office hours and said, I want an optimization problem in this area, I could come up with one. Like this is what I do, right? So literally every area, whether you're going into business or you're thinking about biology or you're going to go to med school or, even the current crisis, I didn't even bring this up, like optimization is all over. Like how do we, have the least number of people infected with this thing, whatever it is, optimization is all over the place. It's in government, it's in nonprofit, it's every industry. Like run a local business, you just run a little cafe somewhere in your hometown, there's optimization. It's a question of whether you treat it the way it should be treated mathematically, or you just kind of do it a little bit kind of approximately, but there's optimization all over the place. The research I do, in a sense, actually involves quite a lot of taking derivative setting equal to 0 or a slightly fancier version of that. So that said, I don't want to do all the different kinds of optimization problems. I want to focus on a couple kinds, because otherwise it gets to be too much to like require all that out of you and to burden you. And one of the areas that actually is extremely useful as creating some concreteness is geometry. And in the past, when I taught this class, like the first 2 or 3 times, I didn't know. I hadn't thought about this, but like I eventually realized students were struggling with the geometry formulas. So it's helpful. Today's point is to review some geometry formulas. Quite a number you will have seen. Some you have seen and those are rusty. And then by the end of class, we'll combine them with other ideas to get formulas that you certainly haven't seen, but we're going to piece together things, I think, in a natural flow today. I should also comment that I think sometimes people get in this mindset of, oh, I like geometry and I don't like algebra, or I like algebra and I don't like geometry. Try to challenge yourself to embrace both as much as possible. They are not technically 2 different subjects. I mean, we do this to create a high school curriculum that kind of works, especially if people transfer to different schools and so on. But they're actually completely connected as subject areas. All right, so let's dig into the geometry. First of all, one-dimensional measures. One-dimensional measurements. Things they go by names like length and width, height, maybe distance. Like how far, how many miles is it to drive from La Crosse to Madison? Things like that. The units on these: inches, feet, meters, kilometers, centimeters, miles. Those kinds of things. And I've got the abbreviations shown there. And that's all I want to say about one-dimensional measures for the moment. We'll come back to one-dimensional measures, but I want to talk about two-dimensional measures, which go by the name of area. So in a nutshell, just like informally, areas like you've got an easel and you're going to paint, and how much paint would you need to just paint an easel solid in one color, right? Like how much paint do you need to paint a wall in a room or a ceiling? Those are the kinds of things that area talks about. The units on area are like things like this. So you can read this as inches squared. So if you read this, using direct wording, cool. Inches squared. You can switch the order and call this square inches. That's fine as well. And this is perhaps one of the most important ideas I want you to think about throughout class today. An area formula always involves multiplying. That's my fancy product is fancy for multiplying. Always involves multiplying two one-dimensional measures. So you might have a length times a width. You might actually just have a length times itself. So it doesn't have to be two different one-dimensional measures. Sometimes it's the same one-dimensional measure. You might have radius, by the way, is a one-dimensional measure as well. So I'm going to have radius times radius. You'll always see this kind of thing going on, of a one-dimensional thingy times a one-dimensional thingy to make a two-dimensional area formula. So let's get going with the one that I'm sure you know, is the area of a rectangle, right? So you've got a rectangle with one side called L, probably for length, and the other side called width, or W for width. And the area, how much paint is needed here? It'd be L times W. Right? So there you see already the one-dimensional measure and another one-dimensional measure. And I think maybe I can clarify a little better in this picture what I mean by one-dimensional measure. So this shaded region in the rectangle, that's like paint, right? How much paint do you need? That's area. But the one-dimensional measure is like that right there. It's like, how long is that string, right? This left side of this rectangle that I just thickened. How long is that string? That's the one-dimensional measure. This all happens to work the same, even if the height and width are not called L and W or H and W, which is whatever letters. So A and B. So I'm using little a and little b for the two sides of this second rectangle, and capital A for the area of the rectangle. So sorry to mix my lowercase and capitals, but I think it's a good idea to try to use the same casing as much as possible, as I'm doing here. Now, I want you to memorize the area of a rectangle, but I don't want you to memorize the area of a square. It's important to know what to memorize and what to build off of the memorized thing. The area of a square should not be memorized because it's just a special case of a rectangle, right? A square is just a rectangle where all the sides are the same length. So I just went with C and C. So following the earlier formula, you plug in C for L and C for W. Isn't the area formula C times C? But C times C you could simplify as C squared. Oh, here's a neat thing. I have it at the bottom of the slide. C squared is actually a sweet AF way of saying this thingy here. Yeah, I wrote and said sweet AF, and that's in the recording. You're welcome. Look, we call this thing C squared, and maybe you didn't think about why we call it C squared, but the language actually comes from C squared is the area of a square where the side length is the base, is the base C. So that the language that we use in algebra of C squared, it was geometrically inspired. The area of a square. Okay, area of a triangle. I think you've seen this formula, but I want to convince you of the formula more than just have it memorized. Is I have this rectangle first, and then if you draw a straight line segment connecting two opposite corners, you have a shaded red triangle. But then you'll notice that if you just flip that triangle upside down and kind of left to right, there's a second copy of that red triangle shown in white. But if these two triangles of the same shape, the two of them together are non-overlapping and occupy the entire rectangle, then the area of the rectangle, if you cut it in half, ought to be the area of the triangle. So 1/2 times the area from before, 1/2 times L times W should be the area of the triangle, right? Okay, and then the next thing is I made a copy of the triangle in red down below in yellow. And I hope everyone can still hear me. I thought I maybe accidentally hit a button here. Okay, so the pop up in the chat and say something if you cannot hear. There's a copy of the same triangle. I just changed the L and W to now be an A and a B. And normally in class, I do a demo where I bring a bunch of books and I show you sort of the spine side of things. And then if I start pushing over the books a little bit, then you would see the spines align and create a different shape. What I did in the computer was I just took this point and I dragged it over, and then I took a screenshot and put it over here. You'll notice then that what I'm trying to get at here is with this I-beam, A is the height over here. It's not this way, okay? It's not that. It's got to be the height of the triangle has to be perpendicular to the base over here. And both of these yellow triangles have the same area. It's still, as before, a 1/2 times a base times a height. Or one of these bases I called B, and then the other, the height, I called A. Now you can write the area of your triangle either in that same fashion over here, 1/2 times A times B, or you can do A times B divided by 2. The point is, either of these two ways of writing it over here, you've got a 2 in the denominator. Okay, so your call which of the two ways you write it. I actually scoured the internet on Monday to see is there an explanation out there for this, and this is not my video. I found this online, and there's this math teacher, and her explanation is actually better than my explanation. So if you'd like to watch the video, go for it. It's optional. It's about 4 minutes long, but I think it's a very convincing explanation of why this area formula still applies to a triangle that looks like that. Okay, now let's talk perimeter. So perimeter means how long does it take? Like, what about if you walk around the outside? So take a look at this rectangle over here. If you start in the upper left corner, you walk along that side. Like, how much string do you need total? Well, there's that L. And then you walk this way, and then so you tack on a plus W, and then we need to add on, you've got to walk up. And so then you get this plus L, and then finally from there you walk to the left, and there's this last piece over here, plus W. So in the end, the perimeter is L plus W plus L plus W. You can leave the perimeter like that, and this is the way I want you to think about perimeter. Often what happens is like terms are collected, so people will tend to simplify, and it's presented in books by like L plus L is simplified to a 2L. That's fine, okay? 2L plus 2W, but it's really important, right, in what we're doing today to not just memorize formulas, but to see where they come from. Some formulas need to be memorized. This is not one of them I want you to memorize. I want you to see where this comes from. I should comment that perimeter is not a it's not a two-dimensional measure. We've been talking about area. There's a one-dimensional measure, right? It's how much string. It's like the length as you walk around. So the units on this, I say this because it happens. Maybe another part of the problem made you deal with area or something. So because of that, sometimes people are distracted and try to report their final answer with units of square inches. But if the question is, what's the perimeter? Then a final answer would be like in inches or meters or miles, not in square inches, not in square meters. Okay, circles. There are two formulas for a circle that you need to memorize. These ones, unfortunately, do need to be memorized. So the circumference, that's walking once around the circle. So it can also be called the perimeter in some circles. Ha ha ha. It is called the perimeter. Yeah, I made the pun on accident last section. That was on purpose. You walk once around the circle, and that distance, that one-dimensional measure, is 2 pi r. What about the area? The formula that needs to be memorized is pi r squared. So by area, I'm talking about how much paint to fill in the inside of this circle, pi r squared. Sometimes people flip these two formulas around, and so I'm going to give you two ways to think about it so you don't flip these around. One is, please notice that the area formula, pi times r squared, or pi times r, is made by, you'll notice, is multiplying two one-dimensional measures. The radius, the length of string here, is a one-dimensional measure, and you have, when you see r squared, you have an r times an r. So it goes back to what we said earlier, that an area formula always has a one-dimensional measure times a one-dimensional measure, even if it's that one-dimensional measurement times itself. It's r times r in this case. That's one way to help sort out which one's the area versus which one's the circumference. The circumference is not a two-dimensional measure, and there's no business. You see nothing here of a one-dimensional measure times a one-dimensional measure. It's just an r being multiplied by a 2 pi. The other way to think about this that I hope is helpful, but listen to the explanation, and if you don't like this explanation, then you can ditch it, you can ignore it, but you can think about derivatives, believe it or not. So there's this circle that's drawn up here, and what about the circle that's just slightly bigger? So I'm going to just kind of draw just around it. I'm trying to draw a circle that was not the greatest, but it'll work. I'm drawing a circle that's just a little bit bigger. And what I want to ask about is, how did the area change? So if you've memorized the area formula correctly, there's a way to check if you've got these two formulas memorized correctly, or if you've swapped. If you have the formula a equals pi r squared memorized correctly, you want to talk about the change in the area. Well, that change is given by slope, right? Change is given by slope. So change in a over change in r, in other words, the derivative. So you could take the derivative here, a prime. Now, you see a pi times r squared, copy the pi, that's a plain number. So constant multiple rule lets you copy the pi. Then you multiply, then you multiply by the derivative of r squared using the power rule. The power rule here is going to give you the power rule is going to give you, differentiating r squared is going to give you 2r. So you've got a pi times a 2 times an r. I didn't write a multiplication dot, but you can, three things multiply together. They're pi and 2 and r. You can swap to write these in any order you want. So 2 times pi times r. So it turns out that the change in the area is the circumference. And think about how that makes sense. If you take the circle that's here, the original smaller circle, and you ask, when you grow the radius a little bit, what is the change in the area of the circle? The change is just the crust of this pizza, so to speak, right? That little bit, that thin layer around, and that piece around happens to be the circumference. It's kind of a neat way to apply the idea that the derivative is not only slope, but is change, because slope is change. It quantifies change. Again, if you don't like that explanation, you can ignore it, but it's kind of a neat way. So my point of this is, it's a spot check. So if you believe you've got the area and circumference formulas memorized appropriately, you could check by differentiating the area formula that you're saying you have, and you ought to obtain what you called the circumference formula. If that doesn't happen, maybe you need to swap the two. Okay, we'll talk now about volumes. So in short, volume is about like how much air could be enclosed inside the three-dimensional region. I've got a coffee mug here, and so the question is how much, coffee fits in here, for instance, or how much air fits in here if the cup were empty. You might have a cardboard box, and ask how much Play-Doh could you stuff into the box. That's what volume is trying to address, and the units, one sample unit would be like inches cubed. You heard me say earlier that an area formula involves a one-dimensional measure times a one-dimensional measure. Well, a volume formula involves a one-dimensional measure times a one-dimensional measure times a third one-dimensional measure. This always happens. So let's take a look. We saw already the area formulas for a rectangle, triangle, and circle. I'm showing them here. And I would like to think of, instead of this rectangle, let's say pasted onto a wall, what if you peel off the sticker and you rotate the rectangle so that it becomes the top floor of a building, and then you just have copies of that rectangle going down lower. So you repeat this, and you would have a shape that maybe, so you've got this rectangle that's up here. I'm trying to depict that over here, and then I'm trying to have my lowest copy of it here, but in the middle as well, I'll try to draw some, but not too many. Like there's a copy of that rectangle here, and then there's a copy of that rectangle directly underneath it as well. And if, like, let's say that you've got 5 centimeters worth of copies of this, then for the volume, you take the area you had earlier and you multiply by that height, h. So same deal, you take the area of a triangle, and if you just repeat triangles, the repeated area, you take that and then you multiply by h. So 1/2 times L times W from before, and you multiply by h. Same deal with the circle. If you have a cylinder, you take the area formula from before and you multiply by h. And so the point I'm trying to make here is the comment, maybe you see it at the bottom or you don't, based on maybe if the controls for the WebEx are in the way, but it says down there, don't memorize these formulas for volume. What's more important to do is understand that all we did was we took the area formulas just above and just multiplied by an h, just multiplied by that direction of repeatedness, how much repetition is going on. Okay, so let's apply some of these, and not in the most usual situations. I'd like to look at problems that I know in the past have stumped people. The 2 questions we look at on this slide are very typical, like mini problems as part of a bigger problem in the kind of things we look at next week. So I'll read the question out. If a rectangular box has a square base, what is an expression for the volume? Now, first of all, we just get to copy a rectangular box, a rectangular prism. We just copy the volume formula from the previous slide, L times W times H. Now, I should actually take a moment to talk about how do you draw a box. One of the last times I taught this class, this had stumped people in office hours, so I think it's worth talking about. First, I draw a rectangle that's kind of slanted due to the 3-dimensional perspective that we're about to add. But what you want to have happen is you want this point here to not be directly underneath this point. Now, this maybe isn't making sense, but let me draw a picture of what you don't want to have happen. So you don't want to have like a drawing where you do, those lines are not even all that straight, but like this point down here is directly underneath this point. So you want to avoid this situation, and here's the reason why. So let me redraw, because this is a little messy already. But if you draw so that none of the 4 points is directly underneath any of the other 4 points, then you make an exact copy of this directly underneath. Let me just draw on paper this tilted version of a rectangle. It's, I guess, technically a parallelogram, but it's a rectangle in perspective. And then just lower your hand and draw the same rectangle. And what you now do is you connect you connect corresponding corners. So like the lower left corner, connect to the lower left corner. The upper left corner, you connect to the upper left corner, and so on. So that's how the box drawing goes. We have the sides of like L maybe is here and W is here. I usually use the height direction, the tallness, like usually there. Whether you swap the W or H isn't such a big deal. You'll see in my diagram, last section I didn't quite have it. In my diagram, it does appear that L and W are roughly the same size. That is what square base is trying to get at. So I know from past experience, people about 2 weeks from now get stuck on WebWork questions and sign into, when you come to office hours, like people are like, I'm stuck. And I say square base, and they go, oh, right, I got to do something with that. So if that happens, I want you to think about this moment, come back to this point in the video. Square base means that L and W are the same number. Now, we don't know what number, but they're the same number. So we're saying L is equal to W. So I'll advance the slide where it's already there. Square base, L equals W. And what that does is it allows us to simplify the volume formula. So you might plug in for the L. You might plug in a W. And then you'd have W times H, which of course you could write as W squared times H. You might, instead of plugging in for the L, you might choose to plug in for the W instead. So what would you plug in for the W? Well, W you can replace with an L. And then you'd have L times H, but I wrote that as L squared times H. So either of these 2 final answers is, I think, as simplified as possible for the info we're given. The answer up here in the first bullet is technically correct. It's just there's an extra variable, and the square base The fact that L is W, and so you can swap one for the other in this problem, is helpful. Why is this helpful? To preview this, spoiler alert, next week, the problems we look at, some of them, the simpler problems have maybe 3 variables. More complicated problems have 5 variables, 6 variables, maybe even 7 variables. That occurs, which I know is going to be a little painful. So the thing is, the more we can get rid of variables, I mean, not just by erasing them, but the more that we can validly get rid of variables by substituting things, it's going to help us out. So I'm just trying to preview this right now, right? So one of the ideas we look at next week, this thought process that we just did, is going to be just one mini step inside a much bigger problem. Okay, one more. Another kind of type of question that we would look at next week. I want you to, maybe we won't look at this specific question, but I want you to think in this way. So suppose you've got a rectangular prism of dimensions 2, 3, and 5, and it has the same volume as a circular cylinder. So you've got 2 different 3-dimensional objects here. One's a box. Rectangular prism is just another language for rectangular box from the previous question. And then the other object is a can. And they have the same volume. Well, okay, and then the rest of the question. Write an expression for the height of the can in terms of the radius. So let's take the one where the object where we were given all the numbers, right? We know the volume, if you multiply the 2, 3, and 5, you get 30. So 30 is the volume of the box, and it is therefore the volume of the can. So we take the can's volume from the previous slide, pi r squared h, and we can replace the volume right there. Since same volume, we get to copy the 30 from here and put it into that spot. And when we do, we'll have 30 is equal to pi r squared h. Okay, so we've used the part now of the question that says these 2 objects have the same volume. Now what we need to do is write an expression for the height of the can in terms of the radius. Now the height of the can is this h. What it means to say write an expression for the height of the can is solve for h. To solve for h, you got to divide on both sides. Now, I say this with no jest or anything like this, but like I have seen people in a situation like this in this class, like in previous semesters, will try to subtract on both sides. You've got to like, this is a very important algebra idea I want to talk about. So sorry if you're really talking about this, but like it comes up. If what you have is multiplication, you have to undo that with division, not with subtraction, right? So don't, if you are allowed to subtract pi r squared on both sides, but it's not meaningful. Nothing cancels the way you want it to if you do that. In order to do anything useful here, you've got to divide to undo the multiplication. So divide both sides by pi r squared. 30 over pi r squared is equal to h. This is one technically good answer. We could stop the question here. So there's a happy face. But to preview something for next week, I'm going to write this in a different way. I'm going to first of all swap the 2 sides. That's not really doing anything much. But in addition to writing the h on the other side, I'm writing it as 30 over pi times r to the negative 2nd power. Now this works algebraically. I hope I can convince you of this. The 30 is still in the numerator. The pi is still in the denominator. What really changed was, instead of an r to the positive 2nd in the denominator, I moved the thing into the numerator, so it's r to the, but then when you swap, right, something from one top of the fraction to the bottom or vice versa, you got to negate the exponent. So where you had a r to the positive 2nd in the denominator, you have an r to the negative 2nd in the numerator. So both of these versions of h, this one and this one, are technically correct. I do like the circled one better. Let me tell you why. It's nicer if you need to do h prime, if you need to take a derivative. So spoiler alert, next week, as one step of the process, we will take derivatives of things that look like this, but I don't want to differentiate 30 over pi r squared. You could, it just requires a quotient rule. So to avoid using the quotient rule, there's this algebra step of rewriting, and then if we were to differentiate this, the 30 over pi, don't apply the quotient rule there, even though it is a quotient, it's just a number. So it's a number multiplied by the function r to the negative 2nd, so you could constant multiple property, you get to copy the 30 over pi and then differentiate r to the negative second using the power rule. So that's way, way nicer than using the quotient rule. So these are some of the big ideas that we're going to apply next week that I'm previewing for you. Cool. So now let's talk about three-dimensional objects, but bring up two-dimensional quantities. So I want to talk about, you start with a box, that's the nicest example, and I want to talk about the surface area. So surface area meaning we're going to take this box and ask, you want to paint the box, you want to paint the outside. How much paint are you going to need? Well, I want you to see that a rectangular prism like this has 6 sides to it. It's just like when you play a board game and there's a dice that has 6 sides on it. Well, that dice is like a little, usually just a little mini cube where all the sides are the same shape, the same square, but you here in this case you just have 6 rectangles. And I want you to see the 6 rectangles and not memorize the surface area formula. I can't stress this enough right now. If you want to tune out and then just wait till the bottom of the slide for when I say the surface area formula, you're going to get yourself in trouble. Like, please don't just try to memorize this. I want you to pay close attention and ask questions. I want you to see that the surface area here consists of 6 rectangles. First of all, the top rectangle, let me highlight it up here, and the bottom rectangle down there. Those are the same rectangle. I mean, they're not the same. Like, it's just one rectangle. You have this literally the same shape and size just directly underneath, right? And both of these rectangles, the area is which of these 3 L, W, H apply? It's the L and the W. So LW for one rectangle area and LW for the other one. So it's L times W plus another copy. One for the top rectangle, one for the bottom rectangle. There's a front and a back, right? So there's a front rectangle over here, which I'll outline. And then there's a back rectangle, back there. And let's talk about those 2 rectangle areas using the LWH that came from this rectangular box. And the front, I think it's where it's easier to see it. There's this side there. I'm trying to draw that thicker right now, is a W, and then the other side over here on the very left is H. So an H times W, or you can flip W times H, I forget what I did in the slide. Yeah, WH for the front and WH for the back. Right? And then do you see the other 2 sides? We've covered 4 out of the 6 sides of this rectangular prism. They can go with useful names. I call them the left and the right rectangle. I think that works here. So there's this rectangle on the left. Yeah, I can shade these this time because they're not overlapping, at least in the picture. And you'll see like the one over here on the left, it's L for one side and then H for the other side. So LH for the left rectangle, LH for the right rectangle. So we've got these 6 separate rectangles. I'm taking care of 2 of them at a time. We should add all 6 of these terms together. LW plus LW plus WH plus WH plus LH plus LH. That is the surface area. I want you to think about surface area this way. Of course, you can combine like terms. LW plus LW, you could write 2LW. Of course, you can do things like that. But it's super important to not just memorize. A lot of books will just present to you surface area formula just like this, and that's it. That's going to get you in trouble with what we do in about 10 minutes. The explanations 10 minutes from now are not going to make any sense if all you just try to do is memorize this without understanding this process. So I'm going to pause. Are we okay with the process? Is there a question? If you've got a question, you should ask. If you have a question, I'm sure somebody else has the same question. So I'll wait for a moment. Okay, not seeing anything. I'm going to look at another surface area question. Again, the ideas we already saw here are going to come up. Like, it's just identify individual smaller pieces of the object and then find those areas and add them up. So here we go. Surface area of a can. A can, I would say, has three surfaces. There's the circle on top, there's a circle on bottom, and then there's a part around the side, so to speak. So the part on top, what's that? So we're talking surface area. Okay, so it's from starting from a three-dimensional object. We're only looking at the outside shell, so it ends up being a two-dimensional thing called area or surface area. But the area on top is a circle, right? So that area is a pi r squared. And then on bottom, the area of the bottom, well, that's the same size shaped circle just directly underneath. So that area should also be a pi r squared. And then what about the side, the part around, the area around? I don't know if I'm making sense with that. I do have a can here, and I'm gesturing to like it's the part around. Like I don't know if that makes a whole lot of sense, and I was worried that it'd be too small in the corner if you've got the video thing showing, and maybe you don't. So I did this on Monday. I created this little video, and I'm gonna play part of it, not even the whole thing. It's a little over 4 minutes. Uh-oh. Okay, there we go. So I do know that you're not going to hear the audio in the video, but because I tested this all, but I said things in the video anyway, so that if you play the video later, you'll hear an explanation. But I'm going to, as I play the video and you don't hear what the video says, I'm just going to narrate what's going on at the same time. So I've got a can. I happen to play the video at double speed. So that part around the side is where the label is. So not the top, not the bottom. Just the part around the side where the label is. Let's find that area. Take a pair of scissors. This slicing actually worked out fairly nicely. It was a fairly clean cut, and I just had to kind of pick at it for a moment. And then there's the part where they glued the label. That gluing was actually, I didn't know where the glue was, otherwise I would not have cut so close. So there was sort of a rip. But take a look at the shape, right? By undoing the label, which is the part around, it's the shape of a rectangle, right? So what about one of the sides of the rectangle? So yeah, is this height? Where's that found in the can? It happens to be the height of the can, right? And now, sorry, the glue was sticking to one of my fingers. And now look at the rectangle. We need the other side of the rectangle, and that I'm gesturing to it on the paper. Where do you find that on the can? And that is found around. That is the circumference, right? So we've got this rectangle, and for the rectangle's area, we need to multiply one side by the longer side, and the longer side, as I wrap it around the can, I hope you're seeing that this is the circumference. I'll stop this video at this point. You can watch the rest of it later if you'd like, but I'm gonna talk. I'm done with the physical demo portion, and I will now say, okay. So there's a link to the video if you'd like to watch the entire 4-minute clip later. But just to summarize, what happened is I unraveled the label. And you end up with a rectangle, and one side of the rectangle is the H from the can, and the other side of the rectangle, which I'm calling currently the width of the rectangle, it's the circumference of a circle. So that brings up the 2 pi r that I said to memorize earlier. So you multiply those two things together, and you could write, I wrote the 2 pi r first and the H next, and I did use some parentheses, so you saw it's really a length times a width, or a height times a base, or the two sides of a rectangle, but it's just all multiplication. So there's no distributing here going on. You just drop the parentheses because it's all multiplications, and you can write them in any order. So I just wrote 2 pi r h, 2 times pi times r times h. So here we go. We've got a pi r squared area on top, we have a pi r squared area on bottom, and then we finally have this 2 pi r h area, and we should just add the three things together for the surface area. This is the way I want you to think about the surface area of a can, the total surface area, when you add these three separate areas together. I want you to know where this 2 pi r h came from, that we multiplied a 2 pi r together with an h. Now, this is not the way surface area formulas are typically given in math books. What usually happens is this pi r squared first term and this middle term pi r squared, people usually collect like terms, which is valid to do. And I'm going to point this out here. If you collect like terms, this pi r squared plus pi r squared ends up being this 2 pi r squared. Of course, the other term, maybe I'll just put this in a box, this 2 pi r h still needs to be accounted for, so it's copied there. However, this simplified version of the surface area of a can Do not memorize it. It will get you in huge trouble. Like you'll get stuck with so many things in what we're about to do. And let me explain in part why. Like I hope what I'm about to say makes sense. There's a 2 here and there's a 2 there, and these 2's are very different. So this first 2, that 2 came about because we collected like terms. There was a very algebra like 2. The next 2, where did this other 2 here come from? It is, if you go back, it was this 2 which came from over here. This is a 2 that appeared only because we were looking at one side of a rectangle. Once we uncurled the rectangle, once we uncurled the label, it was a rectangle. And the 2 is just the 2 that's built in automatically in part of the circumference formula for a circle. These 2's have very different sources. And that's extremely important to understand. If you just try to memorize things, things are going to fall apart in what we're about to do. So I'm going to pause and see, are we okay with this surface area of a can? I want you to think of it like this. All right, so now one of the key reasons to not just memorize the surface area formulas is we're going to talk about cost. In order to come up with any cost formula correctly in what we do next week, you have to understand the surface area formulas. If you just memorize the surface area formulas, things are going to completely fall apart. Every semester somebody wants to ignore this advice. I know, and in office hours we sort it out again. We redo these explanations. I make people explain it back to me. You've got to. Here's the thing, and cost is. What I mean by cost here is that if you are go into any kind of business where you're eventually going to sell something to the public, and the thing that you sell, this, let's say a physical thing you're selling to somebody, and this thing is made up of more than one material. Maybe it's made out of plastic and paper. Maybe it's made out of, there's a cardboard part and there's a PVC pipe part. Anything that's made out of more than one type of material, you've got to account for your own costs properly. And the thing is, cost of material is usually given in dollars per square unit, like when you buy carpet or paint or things like this. So the thing is, we'll start with this small example. Let's say the cost of cardboard is $3 per square inch. I'd like to write an expression for the cost of making a rectangular box out of cardboard. So you've got this three-dimensional object, this box, but the cost rate is $3 per square inch. We already said that the surface area, or the area for short, is here. It's 2LW plus 2LH plus 2WH. Now, what do you do with this surface area, with the area, and this thing that says it's $3 per square inch? What you need to do with the two things, maybe it's not clear yet, but if I'm going to think of some other problem. It's just, I'm going to make up a number, and it's not directly part of this problem, but it helps us think about it. So off to the side, I'm just going to make up a number. I'll just say, I don't know what number what that box represents, but of course it's a number. If we just knew what L, W, and H, if we knew what the variables were, what numbers they were. But let's just say that what that box thing is 100. Let's just say that the area, the surface area was 100 square, and I saw this typo last section. Let's just say that the surface area of the box was 100 square inches. So 100 square inches of cardboard around the outside, and it costs $3 per square inch. So how much is it going to cost to make that box, right? So if it's $3 per square inch, so for each square inch you got to pay this, you should multiply the 3 together with the 100 to come up with a total of, it's going to cost $300. Right? And so if you would multiply 3 by the surface area of 100, if you knew the surface area was the number 300, you should also multiply 3 by the surface area as this formula, even if we don't know the number, right? The process should be the same, that we would multiply. That's the only purpose of making up the number 100 for the moment, is that we learn from this process what we need to do is multiply the cost per area by the area in order to get the cost in dollars. So the cost in this case is you take the surface area from before, And due to order of operations, you got to throw that in parentheses and then multiply by this, in this case, 3, the cost per unit of area. Okay, this idea we're going to see in a couple other examples in a moment. But what I'd like to do is, as a follow-up, because it's a kind of thing that will happen next week, is take this cost we've seen before is often labeled with a capital C, but I'd like to just take this portion, this equation here, I copied it down here, and I'd like to solve for L. It's a very common type of task. So we're following up with a new question. It's a very common algebra thing that we will do next week that I had noticed in the past gave students trouble. So that's why we're going to review it right now. To solve for L, you've got some options. My first thought is to divide both sides by 3, which totally works. But most students' view of doing this is to distribute 3. So I'm going to do that because I think that's what most people end up doing. Either way, it's going to work out. The final answers may look different, but they're technically the same. So if you distribute the 3, you have C is equal to 6LW plus 6LH plus 6WH. Now, sometimes here people try to divide things on both sides. That's not going to help at all. At this point, you've got to look and say the final operation on the right side is pluses, right? So if the final, like earlier we had an example where the final operation was multiplications, and to undo you had to divide. Over here, the final operation is pluses. To undo, these 3 terms, you've got 3 terms, and to undo anything in any which way, you've got to undo addition with subtraction. So you've got to be thinking right now about subtracting or adding on both sides. In the earlier problem we were looking at, you got to think about multiplying or dividing on both sides. So you got to really pay attention to what the order of operations is telling you each side looks like. And so first of all, we've got to think of adding or subtracting on both sides, but what? So we need to solve for L. And I want you to notice that in the equation written, there's an L there, and there's an L right there. The next term, the third term, doesn't have an L. So what I'd like to do is get all the terms that have L on one side and all the terms that don't on the other. So let's subtract 6WH on both sides. You get C minus 6WH equals 6LW plus 6LH. So look, what we did is by choosing what we add or subtract to both sides, we have organized it so that all the terms that have the variable L that we need to solve for, all the terms with L are on one side and all the terms without L are on the other side. Now this is a place where people commonly get stuck. It's a thing I talk about in my algebra class is if you have multiple variables, still don't let this freak you out and don't do different kinds of algebra. Like stick to the algebra techniques that we have. Since there's an L here and there's an L there, both terms on the right side have an L, you can factor out an L, right? So if you factor out an L, whenever you factor, you have to create a new set of parentheses. So on the right side, we didn't do anything to both sides, so the left side looks just the same, but the right side is L times quantity 6W plus 6H. And I should, I guess, comment, like, this always works. If all the terms have the variable L on one side, of course you can factor out. Like, because every term by design had an L, and all the terms that didn't have L were on the other side anyway. Like the fluff was over here on the other side. So check out what this did, right? We went from a situation where there was a line where there were 2 written L's, and now in the next line, the L is only written in one place, right? So we factor because we could. We organized it so that we could factor. But then having factored also created this awesome situation of going from writing L twice in the line above to writing L only once. And now, take a look. You've got to analyze the right side for what's the final operation, and it's multiplication. It's 2 things multiplied. It's L times this other thing, 6W plus 6H. So to undo multiplication, you've got to divide on both sides. And when you divide, you'll have the original left side of C minus 6WH all over 6W plus 6H. That equals L. None of the 6's cancel. None of the 6's here are factors. Okay, I've got 2 more that I want to go through here. So if you have the cost of cardboard is $3 per square inch and the cost of plastic is $4 per square inch, write an expression for the cost of a box with 5 cardboard sides and a plastic lid. So the top over here, this lid or the top of the box is made out of plastic. It's the only plastic side. That's the only side where this 4 is going to count. So the area of the lid, so on top, there's this rectangle on top that's an LW. And so just that portion is going to cost 4 times the area, right? So you multiply those two things together. Just like what we saw before, we just earlier did it to the entire box. But right now, the area of the top is LW, and we multiply 4 times per unit area, so 4 times LW. That's the cost of the top in dollars. The other 5 sides, the area is LW plus 2LH plus 2WH. You see how this is just part of the surface area formula? It's not the entire one. If you just try to memorize the surface area formula without understanding where it comes from, it creates this trouble. All right? So I'm not doing every detail right now, but if the earlier explanation made sense, this is 5 out of the 6 terms. It's the other than the rectangle on top, which we already took care of, was plastic. The other 5 sides are made out of cardboard, 5 cardboard sides. So you take this area for the 5 remaining sides, multiply by 3. You are going to need a set of parentheses to respect order of operations here. So the cost of the 5 cardboard sides all in total is 3 times quantity, LW plus 2LH plus 2WH close parentheses. So the cost of the top, made out of plastic, that in dollars. Here's the cost of the sides that are made out of cardboard. And then we should add these together for the total cost. You got to pay for both the top and the stuff around the sides. Right? So that's total cost. So this is not exactly surface area. This is taking the idea of what's going on with surface area and doing a new thing to it. Every time these questions look a little different, which is why you can't just memorize. Trying to memorize surface area without understanding will create a problem. I've got one last one. Here we have got a can. So the metal for the base of a can costs $7 per square centimeter. And the material for the sides, the round part around, like where the label is, costs $11 per square centimeter. What does it cost for a can without a top? So this can is missing the top. It's like there's no top, right? There's no material, there's no metal on the top of this can. So I have the can here. This part over here is missing. So it's not even part of the surface area we're considering. But what we need to do is look at the base. There is metal down here, and the area of that is pi r squared, area of a circle. And so then you take that area and you multiply by, they say that to make the base, it costs $7 per unit area. So you take the area of pi r squared, multiply by 7 times per unit area, and you have 7 times pi r squared. You could drop the parentheses if you want. And then the area around the side. Remember that was this rectangle, right? So I wrote it with these parentheses, which could be dropped to try to remind you this was a curled shape that once you uncurl, it was a rectangle. So 2 pi r times h. You could drop all the parentheses and just have 2 pi r h. But you take this, and then you multiply by the sides cost $11 per unit of area. So if you multiply these two together, you end up with 11 times 2 times pi times r times h. And you could drop all parentheses there if you want. So then the total cost should be adding together this thingy and that thingy. So I add them together. I just dropped a bunch of parentheses. I wrote in a couple multiplication signs, but there's a total cost of this can. 7 pi r squared plus 22 pi r h. I hope you're seeing why it's super important to know where the surface area formula comes from, to not just memorize. I'm going to end real quick on this. You got to understand rather than memorize most of these formulas. There are a couple that you need to memorize. Please note that cost and area and volume, these are all different kinds of quantities. They have different units. Cost is in dollars, area is in square inches, and that kind of thing. The types of questions we looked at, the numbered questions today, are all warm-ups to bigger questions next week. So, and then I think the other quick comment I need to make is if these quantities are all different, then don't set a cost equal to an area. Don't set an area equal to a volume, and so on. Like, people tend to do things like this all the time accidentally. So these are different quantities that all come into play and work with each other. And I think I should end it with this, just to announce, if you just joined late, to say tomorrow is the date of the exam, though again you pick a 5-hour time frame within 48 hours to work on the exam. So there's no live class. If you sign in tomorrow into WebEx at this time, you are just going to see a visual announcement that says there is no live class. And office hours maybe later today. Otherwise, do the exam, turn things in, and then I will see you next Monday.